Welcome everyone to our September webinar, Flight Dynamics as a Service. My name is Christopher Ulrich. I'm going to be your moderator for today's webinar. I am one of our Space Products Account Executives here at AI Solutions, part of the Free Flyer team. All right, let's jump into it. I would like to take the time now to introduce you to our speaker today, Scott Lowe. So Scott Lowe is our Meridian product manager here at AI Solutions. Since 2013, he's worked on multiple flight dynamics ground systems, products, and also software service contracts, beginning with data coordination software and tools for several Earth observation missions, particularly at NASA's Goddard Space Flight Center. Now, over the years, he's developed routine software for the NASA Tracking and Data Relay System, that's the TDRS network, and also many other innovative tools for engineers across the company and various NASA contracts that he's been a part of. He's currently the product manager for the Meridian Flight Dynamics ground system team. He also serves as the team lead and the technical architect of that product. On any given day, you can find him programming in a number of different languages, from Java and Python to C. He works across AWS, Azure, and different cloud environments. And also, on any given night, you can find him designing different network protocols and essentially also soldering together his next embedded project. So Scott's definitely got his hands full with side projects and is very passionate about this industry. Now, without further ado, I'd like to turn it over to you, Scott, to take the audience through Flight Dynamics as a Service.
Yeah, absolutely. And thank you very much for the great intro. Yeah, I certainly have my hands in a lot of things. But today we're going to be focused on flight dynamics as a service and really this buzzword that we've been hearing a lot over the years, which is the cloud. So we at the AI Solutions company, we really like to focus on solving problems and focusing on need first. So, you know, a lot of times we try to make sure that we're not coming up with systems just to come up with systems. We really focus on what does the industry need? What do flight dynamicists need, right? If you're a mission engineer and you're sitting down solving problems day to day, what do you really need in your tool belt in order to solve problems? So over the last couple of years, what we've really noticed is that there are a number of modern technologies that have been coming out over different cloud ecosystems. You know, this isn't just AWS or Azure or Google Cloud Provider. It's really a huge cloud native explosion of technology. And it's really similar to, you know, when we went from chalkboards to, you know, spreadsheets and actual computing systems for the first time. Suddenly there's all these new tools available. And the problem with innovation, or maybe not so much a problem, but the interesting aspect about innovation is sometimes there's a big learning curve. And so when we're looking at flight dynamics, really what we're trying to accomplish today is identify how can we do mission design analysis and operations in ways that get beyond what we're used to on a traditional computing platform. So, you know, you think about your laptop, sometimes it's such a given that you have a limited set of resources, you don't even think about it. You don't think there's an option where you can run an analysis without a limitation on how many CPUs you have available or how much RAM you have available. It's just always going to be that way, right? Well, that's what the cloud really gives us, is this paradigm where we can escape from those limitations. And so really what I'd like to talk through is our approach. And without further ado, let me get into some quick background. I'm pretty sure most of you on this call will be familiar with either AI Solutions or Flight Dynamics. Take a quick step back. As a company, AI Solutions, we're really focused on space flight. As flight dynamics engineers, we're constantly focused on developing the leading solutions and challenges to solve those challenges for space flight. And over the last 3 decades, as we developed those solutions, we also really focus on continual integration. And what we do is we take all of our latest and greatest designs and we put them into our product, which is FreeFlyer. FreeFlyer, Meridian, we have a number of different tools, but at the end of the day, we're flight engineers at heart, and what we do is we really take those tools with us when we set up in the Satellite Operations Center. And we also recognize that we're part of a big family, right? This industry, as big as it is, it's also really tight-knit community. And so we work really closely with everybody in the Mission Operations Center to make sure that the mission is successful, that the spacecraft is safe. And so we take our tool development really seriously, because it's not just used for us, but it's used to support everybody around us, make sure that products are delivered, that critical data goes to where it needs to go. So a really focused part of our job is actually simulating those flight dynamics. So if you need to know exactly how to get your spacecraft from point A to point B, or to point, L2, or really anywhere in the Earth-Moon system, there's a lot of different trajectories that your spacecraft can take. There's a lot of possibilities out there. And so we focus really hard on simulating those flight dynamics, so that way you have a picture-perfect idea of where your spacecraft's going to be in the future, and even where it was in the past, making sure that everything is accurate. And as you can imagine, especially in something like cislunar space, there are millions of possible trajectories. And FreeFlyer is a very high-fidelity tool, which means that every trajectory it calculates can potentially generate a significant amount of data. And so when you're sifting through trajectories, a lot of times you're doing calculations that are part of a class that we call embarrassingly parallel. And what that means is, if we're calculating a bunch of different trajectories, a lot of times there's not a dependence on each trajectory on each other. And so you can calculate those independently. But the problem becomes if each calculation is taking up a CPU resource and 2.5 gigs of RAM and takes 50 minutes to run. In a world where we are limited to finite resources, you end up in a situation where you have to start time sharing. And you get back to sort of the basic limitation of your computing system. So maybe to bring it home with a more flight dynamics specific example, one of the things that we do a lot of at the company is launch collision avoidance. And, in simple terms, that's just making sure that when your rocket launches and your spacecraft launches, that you're not hitting anything critical. There's a lot of stuff in space, and it's really important to make sure that the launch is successful. So we provide analysis on launch collision assessments. And to really talk about, more in depth about the resource utilization, single launch trajectory, calculating one launch trajectory, this is something that we've done a lot. And it's something that's actually really straightforward process. There's a lot to it, but we've done it so many times that, essentially almost any engineer we have can go through and do launch trajectory analysis. If we're doing a single launch, then it's pretty straightforward in terms of resource utilization. The challenge comes in when we start analyzing multiple launch windows. You can see that, if we have 10 launch windows that we're providing an analysis on, then all of a sudden we're using 10 amounts of the computing resources in order to calculate those different trajectories. So as long as it's not a huge number, not necessarily a problem. Sometimes it's a little bit annoying because we have to spend a lot of time behind our console or run things over a weekend or overnight or something like that. But where the real bottleneck problem starts coming in is when you actually multiply those trajectories. So, if you're doing an analysis on every launch window, but then also an analysis on every spacecraft that's being deployed from each launch window, then all of a sudden this problem starts to get a little bit more complicated. You're having to do a lot more cross-analysis. There's certainly ways that we've optimized this problem. There's lots of things that we do every day to try to optimize problems like these across the board. But one of the things that becomes really, really important is making sure that even if you get to that point of not being able to optimize any farther, that you still have a solution that's going to ensure mission success. So, of course, resource utilization blows out of the realm of possible many times when we look at tracking launches plus satellites plus debris. We all know that there's a ton of debris floating around in LEO. So there's all kinds of things that we need to do to make sure that that we're not running into space debris, that our launch is successful. And of course, this uses a lot of resources to do that. So at the end of the day, we're a flight engineer and we have a complex analysis. We need to solve this problem, but there's probably way too much data for us to deal with in a really easy way. So if we're going to solve this problem, what's our first approach? Well, historically, and this is still done in a lot of mission operations centers today, we phone a friend, right? We take our analysis and we call up our buddy and we say, hey, let me give you a copy of FreeFlyer, or maybe you have a copy of FreeFlyer on your workstation. Can you run this analysis really quick and check it out and give me the data back, right? But in a lot of mission operation centers, you run out of buddies. There's only so many people you can get it into an area. So what some ingenious flight dynamics engineers and other engineers have done is say, hey, let's set up a server. Let's set up a computational resource that's bigger, better, faster, stronger than every other workstation that we have here. Let's offload our jobs there, and then we can use our workstations to really focus on the analysis problem. Well, you run into the same limitation. Sure, you have more resources on your server, but those resources are also finite. And so you can, of course, find a problem that will use up all of your resources. And as you send tasks over to that server and it runs out of resources, you're going to hit that bottleneck eventually. And so, sometimes this helps, but it's never sort of the end all be all getting rid of your resource limitation. So that's really where cloud comes in, right? Cloud is, I like to think of cloud as being infinite resources, and theoretically it's not actually infinite, right? There's only so much compute in the world, but what data centers like AWS or Azure will provide you with is so many resources you couldn't possibly use them up unless you had a problem that was, significantly larger than what all the problems that we have to deal with in kind of like a day-to-day scenario. And so we can always think about a data center as being unlimited resources because it really doesn't limit you. And the problem that we run into is that as flight engineers, we know how to develop complex analytical solutions. That's what we went to school for. Maybe that's what we got our PhD in. Really unique, specialized class of trajectories or orbits, and that doesn't leave a lot of time to learn all the details and the nuances about cloud development or data centers or the nuances of AWS or Azure. And so we have all these resources available, right? Like data centers have them, and they're certainly trying to sell us on using their resources because they're available, and it's a win-win for everybody. But the problem is that we don't have access as engineers because it's such a new technology that not a lot of technologies have been developed yet to put the power into our hands. And so what we've done is we've come up with a system that allows us to essentially take the power of the cloud and link it with the tools that we have available. So effectively, what we call this is flight dynamics as a service. And the concept here is that really what we're doing is we're breaking up the traditional flight dynamics system, which is like a monolithic server environment for running flight dynamics, and turning it into a collection of services. But the really important thing is that when we build these services, we're building them using cloud native methodologies, which means that we're able to fully take advantage of all of the services that are on the cloud. All right, so how are we doing this? We have our flight dynamics engineers, we have a hard problem to solve, and we have a data center. So how do we bridge that gap? So fundamentally, what we're using to power all of our flight dynamics services is a concept called container orchestration. So let's just take a minute and get through the basics. So essentially what we have is flight dynamics software. So we have FreeFlyer, DSTE. There's lots of other tools that we use day in and day out to do our job. And what we do is we package that as a container. You're probably familiar with container technology. Examples of this are Docker, Containerd, Podman. These are all ubiquitous technologies in the sense that, if you have a Linux server somewhere, it has Docker on it already. If you have a Windows server, it takes no time at all to install Docker and run it on there. And so because containers are ubiquitous, data centers have picked up container technologies as being a cloud native technology. So essentially, a container becomes our ticket to ride, so to speak, in a cloud environment. So when we package up our flight dynamics software, now we have a lot of containers, and we can run all of those containers in the cloud because, again, it's a cloud native technology. And so what a cloud ecosystem will do is employ technologies like Kubernetes, Mesos, Rancher, as what's called an orchestration layer. And the orchestration layer is really responsible for running those containers. To think about it in a simple way, if containers are the software executable that your system builds, the orchestration layer is essentially the cloud operating system. So at the end of the day, we package up our software and we run the container on the cloud using orchestration. The benefit to orchestration is that it abstracts away all of the load balancing across computer hardware. So whereas in a traditional approach, if we want to run our software, we would have to take that software and run it on system A or system B or laptop A or laptop B. Whereas with orchestration, we essentially just tell the orchestration layer, I have 500 containers and I need to run all of these and I need to schedule them this way. And the orchestration layer will essentially figure out how many hardware resources do I need to spin up in order to run all these jobs and make sure that everything's executing and completing in a timely way. And this is all part of the data center, by the way. This is the nice thing about cloud technology. The orchestration layer, it's already been built. We don't have to reinvent the wheel. This is something that all major cloud providers are supporting out of the box. If you go to AWS, Azure, Google Cloud, they're all going to have platforms for orchestration technology that we don't have to invent ourselves. All right, so how's this work? So first step is building a container. So essentially, to build a container, what you need to do is take your source code, run it through a compiler, generate an executable, standard software development. If you're working with a Python script, you can skip the compiler step and just deploy your source code directly to the container. But essentially, in any process, you're adding two really specific things to your build environment. You need a container config. This will define the definition of the container and everything that's going into it, including your software. And then you need container build tools. So this is as simple as installing something like Docker on your desktop. And once you have Docker on your desktop, you write a configuration file. You can package up your software as a container. It's actually pretty straightforward. And once you have your container, the nice thing about a container is that you can install all of the system dependencies that you need to run alongside with that container. And this is really what makes containers a cloud native technology, because rather than you having to tell your cloud environment ahead of time what system dependencies you need, let's say you have your software really has this very specific library, or you have some Python code has a very specific math library that you really need in order to operate. You can install all of those dependencies in your container, and then when your container runs, your container already has everything it needs in order to execute. There's nothing that needs to be set up ahead of time. All right, so our flight dynamics container, we put a lot of extra work into making sure that it works and is custom tailored to a flight dynamics environment. So in our container, we put in FreeFlyer. That is our industry leading flight dynamics engine. And we have a number of different system dependencies that we use every day that are helping FreeFlyer, that are helping our algorithm for mission success. And then what we also do is develop a custom execution support software that's aware of the cloud environment. So that way, as your algorithm is running in a cloud environment, it is able to do all of the things that are necessary that wouldn't have to happen on like a local system, for instance. The other nice thing for development in terms of containers is that containers you are able to run these locally. So if I develop a container, I can run them in my local environment just as easily as I can run them in the cloud, and they execute one-to-one. So you know for sure that when you run a container, it's going to be running against the same system dependencies that you'd be running in the cloud somewhere. All right, so now let's get to how we're deploying our container into our orchestration layer. So essentially the concept here is that as we build our container, and then we are shipping our container into a cloud environment and running it on an orchestration layer, and that orchestration layer is responsible for running all of our jobs. So straightforward, makes sense, but obviously there's a lot to making sure that everything's running correctly. So let's get into that. Two concepts that I think we need to understand. The first one being runtime. So when you run a container, it runs just like an executable. You can have containers that are always on. So like web servers or databases are a really good example of this, or jobs. So finite execution. So when you run a container, you can think of it as like if you run the copy command from your command line, you expect that copy command is going to do the thing that it needs to do, and then exit either successfully or unsuccessfully, right? And free-flower mission plans are very similar. When you run them, they perform an analysis, they generate data, and then they exit. So these are sort of the two paradigms that we're building our architecture on top of. So as you can see, the orchestration layer is set up for both. It's able to handle compute jobs. It's doing all of the tasking and scheduling, as we talked about. And then the way that services are handled is in what we call container pools. So essentially, if we have an API or a database or like a data streaming platform, something like that, what the orchestration layer gives us is the ability to turn on or turn off individual database containers as demand increases or decreases. So if we have our flight dynamics engineer and they're making API requests of our system and they're running a lot of tasks, and there's a lot of data that needs to be processed, the database containers can scale up to meet that need. All right, so again, we really like to focus on our tools and solving real problems and making sure that our flight dynamics engineers are front of mind whenever we're designing anything. So when we're thinking about building out a system on the cloud, really what we like to do is just make sure that engineers are able to focus on the algorithm, right? Because that's what engineers are doing best. If you're performing an analysis, you want to have no distractions from that. So we identify two major things as things that are distractors when focusing on that algorithm in a cloud environment. One is familiar software, right? We already kind of talked about this, touched on this, that engineers need to be able to focus on using the tools that they're familiar with and not having to learn a whole new set of cloud resource protocols and things like that, because it's a distraction. At the end of the day, it takes a lot of really in-depth knowledge to understand both sides of the house. And so we don't want the flight dynamics engineer to have to worry about that. The other thing is no limits, right? If you have freedom from computational resource, you're able to do a lot more. So, just think about how you would approach an algorithm development if you were able to say, oh, I can run this on as many CPUs as I want and not have to think about it. So that's what we like to do, is really make sure that those two things are part of our design first and foremost. So looking at our engineer, again, looking at a specific example, let's say we have an algorithm that takes 30 minutes to run and generates 150 megabytes, and we need to run that against 150 permutations. We know that the concept of sharing across computing environments is probably a no-go, not going to work, right? And we know that moving those things to the cloud is where we want to go, but obviously there's some things that we got to solve. So what we try to do is we really try to focus on no installation. So that's kind of like one of our first, one of our first tenets here is not having to install any kind of software in order to get your flight dynamics algorithms to work. You already have FreeFlyer installed on your local computer. We don't want a flight engineer to have to install another tool. You have a browser already. There's no need to come up with a complicated, desktop UI just to handle all of the flight dynamics if we already have access to a browser. So we're designing our system around no installation. And effectively, what we know that we need to do is make all of these things that we would be doing locally available on the cloud. So, for instance, if we run an algorithm, we need to be able to run that algorithm many times. If we're saving off data, typically what we'll do is set up like a file share and run FreeFlyer, generate some data products and put them into like a centralized location that we share with everyone. But the cloud is set up for doing things in a far better way than that, right? So we want to make sure that we have persistent data services available. And last, the thing that makes the integration with our existing tools work is the API. We really need a custom flight dynamics tailored API in order to interact with our tools and do it in a meaningful way and be able to handle the types of data products that we deal with day in and day out on a flight dynamics project. All right, so what do we have at our disposal to do that? On our side of the house, when we're developing a solution, there are two really specific things. Orchestration configuration is one, and pre-built flight dynamics containers are another. So we already went through and looked at what the pre-built flight dynamics containers look like on the inside. But this orchestration configuration is really what enables us to utilize the cloud in, again, a cloud native way. Effectively, what we do is we take the orchestration configuration and the containers and we create a system. And using those two things, once we have that system, we essentially install it into our orchestration layer on the cloud. And that's something that we're doing actively. And again, that's one of the reasons that I really wanted to give this talk today is this is something we're doing every day on Meridian ground system development. We're taking all of our technologies that we have at the company and figuring out ways to orchestrate them and make them available to any flight dynamics engineer that wants to use them. Without having to install anything or set up new tooling structures. So what we do on Meridian is we take that container orchestration configuration, we take FreeFlyer, we bake all of that into a container system, and essentially install that in the orchestration layer on the cloud. We've been able to get it down to a 5-minute install process, which is really nice to be able to just spin up any kind of cloud ecosystem that we want, just running a quick install process. But let's take a look and go through kind of the different aspects of what we need to set up in terms of our orchestration in order to make a tool that works. So the first layer is our gateway. This is things like API, user interfaces, security. So if you have an Active Directory service and you need your flight engineers to be part of that security system, all of the HTTPS and TLS encryption requirements, we need to make sure that we're taking all of that security seriously. And so what we do is we develop common standards that we use on every project that we're developing, and build containers around those things. And so that way we have a solid what we call gateway pool, where anybody that needs to access our system is going through this standardized gateway pool. And again, if the flight dynamicist has a lot of traffic, we have hundreds and hundreds of flight dynamics engineers hitting this API, we can turn on a lot of containers to handle this. But maybe to talk a little bit more in a specific use case, if we just have one analyst who just wants to run 150 algorithms, then it's not necessarily going to require a whole lot of containers. So we'll start with 2, right? We'll just have 2 containers in our gateway, and that should be enough to go on. But 150 simultaneously running analyses can generate a significant amount of data. And so, that's where we're probably going to want to scale up when we get to our data persistence. Again, because we're using these container resource pools, what we can do is scale things up and down, not just on a system level, but like really on a functional level, right? So like if we're getting a lot of traffic from our engineers, and we can scale up those APIs and scale down as necessary. The data persistence, if we're getting a lot of, if we're generating a lot of data because of our algorithms, then we can really scale up those databases. Streaming is another thing that I'll touch on in a minute here, but for now we're not generating too much data that needs to be filtered, and so we don't really need a whole lot of streaming resources. But all of our algorithms can now run, and effectively I'll see if I can show you how the process looks. So if we have 150 requests or to run an algorithm, all of those requests will go from a product like FreeFlyer into our gateway. Our gateway will be able to handle all of those 150 requests, probably store some metadata in our databases, make sure that all of that is working correctly. And then the other thing that our API is designed to do is basically call out to the orchestration layer. And when the API calls out to the orchestration layer, it'll say, hey, I just got 150 requests. Each request requires, 2 or 3 jobs in order to complete. So go ahead and schedule that. The orchestration layer will go ahead and run those jobs. And then as those jobs complete, effectively each one will be able to stream the data back into our streaming service. Take that data stream. If the data needs to go to the database to persist, it'll do that. And then if it needs to go back to the user, it can go back through our API, through our security setup and back into the user's hands. And again, the whole idea here is to allow this to be seamless to the user. So what we're trying to do here is really design a system that is integratable with all of the native tooling that we know and love. All right, so let's take a look inside of our flight dynamics container to get another idea of exactly how this is working. So you've seen in this before. Our flight dynamics algorithm really is kind of the heart of what we're doing. When we develop a container, that is the thing that's running. And so effectively, when that request comes in from the user, and the API says, go ahead and schedule these jobs, that orchestration layer is starting this container. And what it's doing is it's reaching out, starting the container, and then communicating with this custom software. Custom software says, okay, FreeFlyer, I need you to go ahead and load this algorithm in. And then as the algorithm runs, FreeFlyer and the algorithm will continue generating data that goes back into our custom software. Our custom software will stream that back, and the rest. It goes back into our data persistent, back into our API, and back to the user. So to get a little bit more into the weeds on one specific thing before we wrap up, what I really wanted to talk about is data filtering. This is an example of a particular kind of technology that we use called NATS. And what NATS does is it allows you to set up dynamic and highly optimized publish and subscription patterns. So one of the nice things that I'll preview for you in a second here is when your flight dynamics algorithm is generating information. This could be, for every run, this could be, like we said earlier, 150 megabytes. That's not a ton of data, right? I mean, we've all downloaded a 150 megabyte file before, and in this stage of technology, it's not the end of the world to have to do that. But imagine you multiply that times 150. Now we've got a lot of data, and not all of it is meaningful. A lot of times our algorithms will generate data where some of it is really meaningful in one context, but not at all in another. And in another portion of our data is really meaningful in in another context and not meaningful at all. So the way that streaming works is essentially you as an engineer define this as configuration. This configuration file is alterable in your streaming services. So at any time, you can tell your streaming services, hey, I want these systems to publish this information and subscribe to that information. And so it's essentially a linking protocol that allows you to, when your 150 megabytes per run is coming out, the streaming servers can essentially intelligently decide where that information is going. So some of that information is really critical for the user to understand what's happening now. And that information might only be kilobytes, right? If you have small status messages, flags that you're looking for, if you're doing like a collision analysis and you're only interested when you have some kind of flagged event that you want to be notified of, you don't need to see every single data product. In legacy operations, we're so used to having to have the entire data set at our fingertips locally in order to make meaningful data of anything. That with systems like this, it's easy to overlook that we actually don't need everything all at once. And so that's what effectively what the streaming service does is it says, okay, take this chunk of data from the whole chunk and send it over to data persistence. We're going to keep that on the books. This chunk is status, send it back to the API, and the API can communicate that information back to our flight dynamicists. Or if you want to do like a reconstruction of maneuver or something like that, often you don't need all of the data. You just need specific windows of data in time. And so you as an operator or an analyst really want to be able to say, hey, I just need time window start through end. And that's where when you communicate with your API, the API can use the streaming filters that have been provided to give you specific windows of time that have been set up in database persistence. So again, that way you're only getting what you need, and you can get it in real time. So like as things are generated, you don't have to wait for the run to be complete. That run can publish things in real time. So, again, I would love to talk in much more detail about any one of these systems. So if anyone is interested in any aspect of the things that I've been talking through today, again, we design these types of systems day in and day out, and are always, happy to kind of geek out and just talk through things. Yeah, feel free to reach out at any time. I think I have some closing remarks here. Probably get through those. Yeah, I sure do. All right, cool. So yeah, the big takeaways that I really wanted to kind of touch on was that modern computing environments, they're available, right? Like we have access to these for very little money, compared to what we spend on legacy hardware. You can spin up resources tremendously easily, sometimes in the matter of minutes or hours. And so it seems kind of silly that a lot of times we're just like leaving these technologies on the table and sort of reinventing the wheel when we're trying to come up with solutions. And so really what we focus on Meridian and at AI Solutions is we try to focus on technology development strategy that allows us to focus on what technologies are really going to be enablers, like game changers for the flight dynamicists that are out in the field. Doing the real work of making sure that missions succeed. So, there are a number of different, flight dynamics topics that really do actually require this type of technology. I know, I've been working with a number of different people internally here that are looking on the horizon and saying, hey, we're going to need to be able to do these massive calculations. How are we going to do that? Constellation management, cislunar navigation, being able to do like all kinds of different trajectory planning, advanced techniques it's just really, really critical to be able to have technology that supports you. So. Yeah, so I think it's time for Q&A. Chris?
Hey, Scott, thank you. Really appreciate the time here today. Thank you for this presentation. And yes, we would like to open the floor now to questions and comments from the audience. Please feel free to use the Q&A function. The team here will monitor the chat. Next couple of minutes, we do have some time for questions, so feel free to ask those now. And Scott, thank you again for the presentation.
Absolutely. Like I said, anytime if somebody has a question that they think about after the meeting, man, I'd love to talk about this stuff.
Yeah, absolutely. To that point, we'll share some information in a moment about how folks can get in touch with us as well. It does. Let me just take a look at the questions here, Scott. So one question that kind of was brought to our attention is around orbit determination, right? And how a capability like that, particularly something along the lines of like shadow calculations. Could you talk a little bit about how flight dynamics as a service kind of plays into those types of capabilities and the amount of potential data that's needed to solve those calculations?
Yeah, it's a really funny question. A friend and coworker and I were just working on this this problem recently. So when you're trying to calculate things for like drag estimation, when you're trying to calculate like the area that is going to be impacted by things like solar radiation and others, um, taking the simple act of just taking a three-dimensional object and breaking it down to like a 2D area can take a long time and generate a lot of data. I think we were looking at the process that we were trying to optimize started out generating 2 gigs of data and took something like 15 hours to run. It was not a simple calculation to be able to do that. And we were able to optimize it. We were able to like take that algorithm and get it down to 25% of that. So it was 500 megs. It's significant savings, but you're still dealing with like a large amount of time to process that. And so sometimes the automation aspect of a cloud environment is really all you need. Like there's a lot of advanced technologies, right? Like sometimes you need AI, sometimes you need lots of different cloud native buzzwords I could throw out. But really sometimes it's just being able to say, okay, I have 3 or 4 of these calculations that I need to do, and I don't want to have to manage these. I need to put them into a system that's able to aggregate, collect the data, and do everything. Because there's a lot of it. Sometimes free flyer takes a while or free flyer, the algorithm itself can sometimes not be the thing that takes a while. Sometimes it's the post processing of that data, right? Free flyer is a high fidelity tool. It generates some significant data sometimes because there's a lot of detail in the data. And being able to post process that and turn that data into like meaningful information is really what you're after. I mean, that's what we do as flight dynamics engineers is figure out, what's meaningful about the situation based on the data. So automation, being able to take those jobs and essentially offload them from your workstation onto something that's running is a really basic utility that's just invaluable.
Yeah, thank you for that.
Sure.
We do have another question here from the audience as well. Could you explain a little more about the orchestration models, particularly in terms of let's say you have different types of missions, different sizes of satellite constellations. Could you talk a little bit about a little deeper kind of into how the orchestration models would work in terms of those different mission sizes?
Yeah, so just like software development, we handle things on sort of like a layer by layer basis. So our software in general uses really common industry standard paradigms. So for orchestration, Helm charts are a go-to, right? So when we're setting up a Kubernetes system, we're going to use something that's standard across the industry that other people are understanding. But then what happens is we get into individual nuances and details, and that's where it becomes less important to be standard and more important to be flexible. And so as we go through those layers, we sort of make trade-offs along the way about, okay, how flexible do we want to be versus how standardized do we want to be? So the way we develop our flight dynamics technology, and this kind of goes back to what I was saying about being like really custom tailored development shop, is that we will use these open standards that are well known in the industry for being cloud native. And so at the base level, yes, we can deploy, a very large number of containers using orchestration because we didn't have to invent that technology. But our containers themselves will have the custom technology that we need, but we also make those customizable. So that's actually one of the features that we've been talking through on Meridian has been being able to swap out free flyer procedures. So when we develop a container, certain parts of that container are fixed, but certain parts of that container we leave intentionally open so that way a user can go in and actually change the code in that container and make that run. We've looked at things like linking up the code inside an individual container to repos. One of the challenges that I think missions run into a lot is that they're not static, right? If we deploy to a ground system and we use one type of model, in our orchestration, that model may have to change over time. So what we've kind of been, I'm sort of proud about this too. I think one of the things that we've gotten really good at over the last decade has been looking at how missions have changed over time and being able to make sure that we're flexible in the ways that the mission is changing. So I hope I'm kind of answering the question about the model. Again, this is like very top level, 10,000 foot view. This is our approach for strategizing how we can have a flexible model.
Yeah, no, that's great, Scott. Thank you.
Yeah.
Let's see here. I think we've got time maybe for one other question here. From the perspective of, let's say a customer is thinking about their data strategy, right? How important is a data strategy when sort of contemplating a flight dynamics as a service? Can you talk a little about that?
Yeah, I mean it's critical. It's foundational, right? I mean, I think that's what we need to do as flight engineers is look at what is our data generation going to look like. I think one of the other things that we've learned is when we're working with containers, sometimes it's better to handle a container run as like a batch of data. So we're going to run this whole mission plan. We're going to generate 150 megabytes of data or 2 gigs of data or whatever it ends up being, and then run like subsequent processes that operate on that data. Sometimes we need to get really, really low level. And, like when we're working with like a numerical integrator, sometimes it's really important that every loop of that iteration works with other containers. So there's sort of like different technological approaches that we have to apply to those different scenarios. And oftentimes those are data dependent. So it really requires you thinking about that data before you go into your design process. But again, that's why we sort of handle things on layers, right? Is that we design these open standards that we're using and we can help other people develop, as well. Like that's something that we also do a lot of is customers will come to us and say, hey, we want to design this type of container. What would you guys do? And we help out. We make sure that we're all in this together, right? And so that's that question is just a really good one because that's one of the things that I specifically talk about every time we're talking about how to implement a new container solution is let's look at what kind of data you're going to generate because it affects what your design is going to be.
I have one more question for the audience here. I think we're still doing good on time. Could you please elaborate a little more on the limitations of the orchestration layers, particularly with LEO and HEO constellations, maybe compared to those within cislunar space or deep space, Mars missions? Can you talk a little bit about, in terms of like orbital dynamics, maneuvering, autonomous decision making?
Yeah, I think some of the things that you get into with more of the autonomous decision making, again, it's easy to start thinking about artificial intelligence and some of the bigger technologies that we run into, but a lot of times the simple problem solves it. I think one of the big limitations that we run into in flight dynamics is that sometimes problems aren't parallelizable, right? We have large classes of problems that are, and that's what this conversation is all about, is solving a lot of those. But there are certainly a large amount of problems where you can't just split the problem. It has to be sequential, and then you're looking at optimizing it. And sometimes there's limitations to how much you can optimize that. And so orchestration is not the end all be all. There are some things, when we talk about running containers in parallel, where it's like, you expect that when a container runs, it's going to take minutes, not microseconds, right? Whereas sometimes you have calculations. I know we did some mission design on MMS that used GPU technology, and that GPU technology was what we used to like enable them to be able to meet their time requirements. But that's only because we were able to do those calculations at such a low level. So we certainly run GPU technology in a container and include that as part of orchestration. But orchestration is not a good way to solve that particular problem or that particular class of problem, right? It's much better at handling like the sort of en masse stuff. I always think about it as in terms of, if you have 1 million users and they're all trying to stream video from Netflix, right? And you need to transcode a large number of videos. Containerization really good at handling that kind of problem. But yeah, when the scale changes in terms of like how quickly you need things to operate, things like that, that can make a difference.
So it's very dependent on mission by mission scenarios, right? That would help kind of steer the direction of that involvement.
Yeah, and that's a game that we're constantly playing on Meridian is looking at like, okay, in not just in mission by mission, but like, hey, this mission has these 3 different scenarios, and we need one approach for one scenario, another approach for another scenario.
Awesome, cool. Folks, I just want to thank everyone for their time, but before we go here today, I just want to quickly let you know that the Free Flyer team will be in Bremen, Germany, for Space Tech Expo. I want to pull up a slide here quickly now. If folks are going to be at the expo and would like to come visit us, please feel free to scan our QR code. You can book a demo with us or chat with us at the conference. We're really excited about that. So I'll leave this up here for a minute. Again, Scott, I really just want to thank you for your time. I think this was a really great conversation. I think we're really starting to think ahead about the future of flight dynamics, right? And the impact that these processes, these missions are going to have on the the amount of resources that we have, the amount of data that we're using, and ultimately the people, right? The end users, the engineers who are going to be working on these complex problems and who are a part of these systems. So I think this is a very timely conversation. Feel free to reach out to us. You can contact us at sales@aisolutions.com. You can also visit us at freeflyer.com. AI Solutions is the company. As a reminder, Free Flyer is our flight dynamics software. So thanks to all for being part of this presentation today. Scott, thanks to you again. And yeah, great conversation. And we look forward to many more of these presentations, hopefully as Q4 and the new year rolls around as well.
Thank you very much.